Hi, my name is Amy Sullivan, and I'm the current president of AAAR. It's my pleasure to welcome you to the 35th in our monthly AS&T lecture series. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. So each month, the editors of AS&T select a high-impact paper to be presented by its authors. With these lectures, we hope to be able to tie our journal to other activities, highlight the amazing research happening in our community, and also give us a chance to meet outside of the annual conference. These lectures are being recorded and will be posted later to AAAR's YouTube channel, which you can access from the AAAR website under the Events tab. In addition, each of these lectures is being hosted by one of our student chapters. With that, I want to thank everyone who's helped to make these happen and all of you for joining us. And now I'll turn it over to our student chapter from the University of Arizona. Thanks.
Hi everyone, my name is Taiwo Ajayi. I'm the student chapter president for AAAR, and I'll be introducing our guest for today, Dr. Alison Bain. She's an assistant professor in the Department of Chemistry at Oregon State University. She obtained a BSc in chemistry from Carleton University in 2013 and an MSc in chemistry from the University of British Columbia, and a PhD in chemistry from McGill University in 2021. Following a PhD in 2021, where she began working on aerosol science, sorry for that. Following a PhD, she worked as a postdoctoral researcher at the Bristol Aerosol Research Center at the University of Bristol until the fall of 2023, when she began her independent career at OSU. Her research interest lies in understanding the physical properties of aerosol particles using a combination of single particle spectroscopy, macroscopic measurement, and physical modeling. And without further ado, I would like to hand it over to Dr. Alison Bain. Thank you.
Thank you for the kind introduction and also the invitation to speak with you all today. So the paper that was selected this month is actually a review paper where I look at the recent advances in experimental techniques for investigating aerosol surface tension. And there are quite a few techniques that have been developed in the past years, many of which have been just recently developed, but others that have been improved upon for aerosol research in the past few years. And so before we get into all of those different techniques, I'd like to start with a bit of introduction and background about aerosol, about surface tension in general, and then why we should care about it for aerosol research. So first of all, what is surface tension? Well, if we have a bulk liquid or an aerosol droplet with some bulk to it, the molecules in the bulk of that droplet or of that beaker of solution have pretty much equal intermolecular forces around them at all times, at least if we were to average over time. However, at the surface, because the symmetry is broken, the molecules at that interface do not feel the same forces from the top as they do the bottom and the sides. And so at the interface, we have these unbalanced forces resulting in a higher surface energy at the surface than in the bulk. And so surface tension is sometimes described in units of joules per meter squared. And that is referring to this surface energy at the interface that is higher than in the bulk. An equivalent unit is newtons per meter. This is another unit we'll see surface tension recorded in. And this is a force per length required to create a new interface. Now, due to the strong hydrogen bonding network of water, water droplets or water in general has quite a high surface tension of about 72 millinewtons per meter. But if we're talking about aerosol, quite often we're talking about solutions that do not just contain water, but they have some solutes in them. And these solutes can impact the surface tension. So for example, inorganic salts, which are shown here in this region G, can increase the surface tension of water as we increase the concentration of that salt. And it's going to require approximately molar concentrations in order to see a change in surface tension. If we move to something like a soluble organic, let's say carboxylic acids, they're this region E here, they can decrease the surface tension when we increase their concentration in water. But again, we're seeing sort of molar to tens of molar concentrations required to see any change in surface tension. We also have what we would consider to be strong surfactants organic molecules that preferentially partition to the interface of an aqueous system. And these are sort of over here in this region A through C. And sometimes these molecules can reduce the surface tension of our droplets in concentrations even on like the micromolar to millimolar concentration range. Now, why should we care about surface tension in aerosol droplets? Well, actually, surface tension can impact all sorts of different aerosol properties. So for example, if we're talking about respiratory aerosol, the surface tension is going to impact how these droplets spread on surfaces, and that can in turn impact how they dry and the eventual crystals that are formed. In this bottom panel here, we see the morphology of spray-dried particles after they have dried. And as we go from panel A to panel H, the only thing that has changed is the amount of surfactant in that solution. So we can see that increasing the amount of surfactant in our solution can drastically impact the morphology of our spray-dried particles at the end. And surface active molecules in aerosol, especially like sea spray aerosol, can also impact the eventual formation of clouds and the hygroscopic growth of aerosol. So for example, if we look at these polar curves here, if we have particles that are just made up of salt and these dotted lines, we can see the activation barrier is quite high. But for the same size particle, if we have the addition of some surface active material, the activation barrier for cloud formation can decrease. Surfactants at the interface of aerosol particles have also been shown to influence interfacial chemistry. So in some cases, it can increase yields for surface reactions. In other cases, it can decrease yields. And so this is another interesting area where surface tension and surface active molecules are of interest in aerosol research. Now, you might be asking, why can't we just measure the surface tension of a beaker of solution and use that to predict the surface tension of an aerosol droplet? Well, there are a few reasons for this. And first is that our aerosol droplets, of course, can exist in metastable states because they are suspended in a contactless state. So our aerosol droplets can be supersaturated or supercooled, which are very difficult to achieve in a beaker of solution. Also, in our aerosol droplets, because they are quite small, we have an increased surface area to volume ratio compared to a bulk solution. So here in this table, I just have some different radii. So if we go from about a millimeter size down to about a nanometer size, we can see that the volume of those droplets changes from microliters to attoliters, and the surface area to volume ratio is going to change by orders of magnitude. So one thing that can happen when we move from a bulk solution to a high surface area to volume ratio droplet is that we can get bulk concentration depletion. And this occurs because of the huge difference in surface area between these two systems. So let's say we had a beaker of solution sitting on our benchtop and approximately 100 milliliters of solution in there. Our air-aqueous interface at this beaker would be on the order of about 20 square centimeters. But if we were to aerosolize the solution and create 100 milliliters of 6 micron radius droplets, which have about 1 picoliter volume, our surface area would increase by orders of magnitude. Now, if we have surface active molecules in both of those solutions, both of those systems, both the beaker and that aerosol droplet suspension, those surface active molecules are going to have to partition to the interface to reach an equilibrium between their bulk concentration and their surface concentration. And just because there's more surface area in those droplets, the partitioning is greatly altered. So one thing to remember when we're talking about the total surfactant concentration is that the total concentration is that moles of surface active molecules on the surface plus the moles of those molecules in the bulk divided by the total volume. So if we're talking about a beaker of solution, the moles of surface active molecules at the interface can be negligible. And so it's really the total concentration is equal to the concentration in the bulk divided by the total volume. But if we move to an aerosol droplet where we have a high surface to volume ratio, the moles of the surface are not negligible. We have to consider these. Another property that can be affected when we move to these small droplets is the dynamics of surfactant partitioning. So when a new interface is formed, it's going to take some time for our surface active molecules to first diffuse to and then absorb to this interface. So in this plot down at the bottom here, we have some macroscopic dynamic surface tension data. We see at time 0 or very close to time 0 when the interface is formed. We have a high surface tension, close to the surface tension of water. And then it takes some time for the surfactant molecules to make it to the interface and reduce the surface tension towards its equilibrium volume. Now, because we can have bulk depletion in our aerosol droplets, as well as we have this curved interface for our molecules to diffuse to, the timescale of the surfactant partitioning can be impacted when we move to a droplet phase compared to a macroscopic solution phase. Okay, so now we're going to start going through the different techniques that have been developed or used in the field to measure the surface tension of aerosol. And we have 9 techniques to get through. So here we go. The first one I would like to talk about is pendant drop tensiometry. And this is probably one of the most used techniques in the aerosol science literature. In this technique, we have a syringe that's full of our sample, and then we form a droplet here at the end of this blunt needle. And we're going to collect images of these droplets. And so we have our light source and our diffuser, and we're going to collect the image on this camera. We end up with a photo or an image that looks something like this, and then we're going to fit the outside shape of this droplet with the Young-Laplace equation to determine the droplet's surface tension. And this has been used in a lot of different contexts in aerosol science. So for example, people have looked at chemical reactions that can occur in aerosol and looked at how surface active are the reaction products. So that's what we see here in this first example, a 1-to-1 glyoxal and methyl glyoxal mixture in water, and then also in ammonium sulfate solution, and looking at how surface active are those products depending on how much organic went into the reaction. Another place where pendant drop tensiometry is used quite a bit is when people go out to the field and they collect aerosol samples on a filter. They'll bring them back to the lab, do an extraction, and then measure the surface tension of that aerosol extract. So that's what we're seeing here in the right-hand side of this slide. We have the surface tension of some aerosol extracts of sea surface microlayer, as well as sea spray aerosol from a couple of different locations. Pendant drop tensiometry can also be used to measure surface tension dynamics. So we can create this droplet on the tip of our needle and then continue to take images as a function of time. And so that's what we're seeing here. We have the time-dependent surface tension, and they've looked at a few commercial surfactants as well as aerosol samples. And what they found here is actually most of these aerosol samples, their dynamics behave quite similar to sodium dodecyl sulfate or SDS, rather than some of these other surfactants. So pendant drop tensiometry, we mentioned that we can look at dynamic surface tension as well as equilibrium surface tension. It requires quite small sample volumes. So we're talking about microliters of solution, but these droplets are on the millimeter size range. This technique can be used for looking at either transparent or light absorbing solutes. However, some of the downsides are that this is a low surface area to volume technique. So we would consider this more of a bulk surface tension technique than an aerosol droplet technique. And our droplet is going to be in contact with a needle and that reservoir full of liquid in the syringe. And so we're not really in this high surface area to volume ratio. Another technique that has been used in the literature quite a lot is atomic force microscopy. And in this technique, they have their AFM cantilever tip and they grow a nanoneedle on the end of that tip. And that nanoneedle is going to be used to come in contact with an aerosol droplet that is on a substrate. And then they're going to pull back that cantilever tip and determine what the retention force is and use that retention force in order to determine the surface tension of the droplet. So this technique has been used quite extensively, but one of what I would say is one of the coolest applications is to look at aerosol that has been generated from a sea spray aerosol, and they collect it on a filter, and then they can measure the surface tension of individual droplets. And so what we see here on the bottom, we have surface tension as a function of days of experiment. And during this experiment, they were looking at aerosol over the course of time where there was 2 phytoplankton blooms. And then all of these red triangles are individual surface tension measurements. And so what we can see is by measuring every single droplet, we notice that the surface tension of every droplet is not the same. Some of these droplets, we have an increased surface tension compared to water, so they probably contain more salt. And some of these droplets have a decreased surface tension compared to water, and so they probably contain more surface active organics. So one of the big pluses of this technique is to actually be able to measure the surface tension of individual ambient aerosol droplets rather than just an ensemble average, which we get when we take an extraction of a filter. This method is for equilibrium surface tension, and we can look at very small sample volumes. So I believe the smallest size particle they've been able to look at is about 250 nanometers, which is right in the ambient aerosol size range. This technique is useful for both transparent and light-absorbing solutes. However, our droplets are going to be deposited on a substrate. If we get to very high viscosity droplets, we start to see large discrepancies. And it's also important to keep this nanoneedle tip clean during the measurement. If it is dirty or some sort of salt was encrusted on it, then the next measurement would not be a very good measurement. The next technique I'd like to talk about is droplet deformation. And in this technique, they're going to use the optical forces from 2 laser beams, which are coming in from opposite directions to this trapped particle. And the trapped particle is going to be at the shared focal point of those 2 lasers. And as the power of these lasers are increased, they can actually deform the droplet into an ellipse. And when an ellipse is formed, the whispering gallery modes in that droplet become split. So when we have a sphere, we have symmetry in all directions, but when we turn that droplet into an ellipse shape, now we can split those whispering gallery modes. And so Rafferty et al. Collected whispering gallery modes from 2 different angles, so the 0-degree scattering and the 90-degree scattering. And that's what we see here in this plot C. And as we can just kind of see, there's this tiny little split between those modes due to the break in symmetry of their aerosol droplet. And they can use this split in whispering gallery mode positions to back out the surface tension. And so in this example, they have looked at sodium chloride at 62% relative humidity and citric acid at 86% relative humidity, and were able to quite accurately determine the surface tension of those droplets. So this technique has been used for equilibrium surface tension measurements. They're looking at optically trapped droplets, so we're in the sort of picoliter size range. Because we're working in an optical trap, the solute of interest needs to be transparent at the laser wavelength. So if we had something that absorbed at their 532 nanometer laser line, then the droplet would no longer remain trapped in the optical trap. This technique has the possibility to look at viscous aerosol because the ramp in laser power could happen at any rate. And so while the viscosity would slow down how fast that deformation happened, we should still be able to measure the surface tension for high viscosity droplets. Now, some of the downsides here are that optical deformation is quite small, even for high laser powers. And during their experiment, as they increase the laser power, that droplet is going to be heated. It also turns out that it requires very precise knowledge of the particle relative to the laser focal points, which is not always easy to figure out. However, these shortcomings or these difficulties have been largely overcome in a recent paper by Shahabadi et al., where they use an electric field to deform the droplet rather than an optical field. And so if you're interested in that, I would recommend you check out their paper. The rest of the techniques that I'd like to talk about today all rely on these surface oscillations of droplets. And so when we have a droplet and it's oscillating, we have this L equals 2 mode, which is going between a prolate and an oblate ellipse. And then we have an L equals 3 mode, which is a little bit more complicated, and L equals 4 mode, which is a little bit more complicated still. But what we can see in these bottom two panels is that the L equals 2 mode has the highest amplitude, and it also remains oscillating for the longest. So the L equals 2 and the L equals 3 mode, they begin to damp while the L equals 2 mode is still oscillating. If we perform a fast Fourier transform over this oscillation, we can determine the oscillation frequency of a droplet. And there are a number of different ways which we'll look at in the next few examples of how we can determine this oscillation frequency. But the surface tension of our droplet is going to be related to that oscillation frequency, omega, as well as the radius of the droplet and the droplet's density. The denominator of this equation here depends on L, which is the mode order that we're looking at. So a technique that I used during my postdoc was droplet coalescence and elastic backscattering. And in this technique, we are going to start by holding 2 droplets in our optical trap. And then using the spatial light modulator, we're going to be able to bring those 2 droplets closer and closer together until eventually they meet and they coalesce. This coalescence event starts the droplet oscillating in the trap. And if we collect the time-dependent elastic light scattering, we can start to see these oscillation frequencies. A fast Fourier transform gives us the oscillation frequency, which we can fit with a Lorentzian function. So this is our L equals 2 mode. And then at the same time, we're going to collect the cavity-enhanced Raman spectrum. So that's what we see down here. We have our broad water Raman stretch. And then we have our whispering gallery modes on the top of that, which we can use to determine the droplet's radius and refractive index. So the last thing we need to put in our equation is the droplet's density. But if we have the refractive index and we have some parameterizations, we can easily get the concentration of the solute as well as the droplet's density out of this information. So we've used this technique to look at the surface tension of a number of different types of droplets. So this first example, these are low molecular weight organosulfates. They're quite soluble, and so you see that it's requiring molar concentrations in order to reduce the surface tension in both of these examples. But we've also been able to look at the surface tension of droplets containing strong surfactants. So in this example, if we start here on the left, we have our lowest surface activity surfactant, so it has the highest critical micelle concentration. This is octyl B thioglucopyranoside. And we actually see that our macroscopic measurements in black and our droplet measurements in red follow a very similar trend. However, when we start to move to more surface active surfactants, like this tween 20 in the center, we see that it actually takes more surfactant to reduce the surface tension of a droplet to the same surface tension compared to our macroscopic solution. And when we move to the most surface active surfactant that we studied, the C16E8, now it's requiring orders of magnitude more surfactant to reduce the surface tension of a droplet compared to when we measure it in a macroscopic solution. So in this example, we're seeing that bulk depletion start to come into effect as we move to these stronger surfactants. So the information that we've been able to pull from these measurements has allowed us to measure the surface tension of these strong surfactants, as well as surfactant mixtures, and how the size of the droplet, so the surface area to volume ratio, impacts this partitioning. And using these novel data sets, we've been able to test a number of surfactant partitioning models, which account for the surface area to volume ratio of the droplet and then make predictions of surface tension from macroscopic solution measurements. So our droplet coalescence and elastic backscattering technique allows us to look at small sample volumes. So we're talking picoliter volumes here. It's possible to look at both supersaturated and subsaturated solutions in our optical trap. And we've been able to look at the size-dependent surfactant partitioning with this method. A major drawback, of course, because we're working in an optical trap, is that we can't look at any sort of light-absorbing solute at our laser wavelength. Another technique that I worked on during my postdoc was stroboscopic imaging of aerosol droplets. And in this technique, we're going to generate a stream of identical droplets using our droplet dispenser. And we're going to image them stroboscopically using a high power LED, and then this combination of objective, zoom lens, and camera. And the experiment works by generating the stream of droplets at a known frequency, and then stepping up the time between when our droplet is dispensed and when we snap a photo. And so what we're going to end up with is a number of photos that look like this, and we're taking a photo of each droplet, but at slightly different times during the trajectory, and so we can kind of see what is going on as a function of time. From these images, we can use the calibrated pixel size of our camera to determine what the size of the droplet is in the X direction and the Y direction to determine the droplet's aspect ratio. And we use this aspect ratio trace as a function of time to do our fast Fourier transform to get the oscillation frequency, which we see here in panel D. Now, because our droplet has surfactant in it, we're expecting to see some dynamics as that surfactant partitions to the interface. And so what we've done is we have taken a splice at each of these vertical lines here and fast Fourier transformed everything to the left. And so what we see in panel D here is the fast Fourier transform of all of these different splices. And we can see that that oscillation frequency is moving to lower frequencies as the surfactant partitions to the interface. And when we then calculate our surface tension, that's exactly what we see. Our surface tension starts at a high value, and as time goes on, it begins to decrease as that surfactant partitions to the interface. Now, if we have a system where we don't expect any dynamic surface tension, maybe something like pure water, when we take our Fourier transform of the different splices, we see that our oscillation frequency remains constant, and then our surface tension also remains constant as a function of surface age. So we've been able to use this technique to look at a number of different systems. So here, for example, we have different concentrations of a strong surfactant, sodium dodecyl sulfate. And we've also been able to explore partitioning models that take into account the dynamics of surfactant partitioning. So overlaid here are some model lines for a kinetic model that we use describing the surfactant partitioning dynamics and then comparing them to these droplet measurements. The microdroplet dispenser technique has been also compared to optical tweezers for the case where we don't expect any sort of dynamic surfactant partitioning, and so that's what we see here on the right. So this example is different ratios of sodium chloride to glutaric acid. So the stroboscopic imaging technique can be used for dynamic surface tension for systems where we expect surfactant partitioning to occur. It can also be used to look at equilibrium surface tension if we are thinking about soluble solutes, like this example of sodium chloride and glutaric acid. We're still working with small sample volumes, but these are definitely greater than picoliter. We're talking tens of microns in this case. And there is a possibility of working with either transparent or light-absorbing solutes. And we are in a contactless environment here. Now, some of the drawbacks of this technique are that after we generate our droplet and those surface oscillations are excited, they are going to damp, and the time scale of that damping is directly related to the size of the droplet. And so as we move to smaller and smaller droplets, the time scale that we can see these oscillations on gets smaller and smaller. Because we're working with droplets that have been directly dispensed out of this droplet dispenser, we can only work with subsaturated solutions and also low viscosities because this droplet dispenser doesn't work for high viscosity solutions. The next technique we'll talk about is rainbow refractometry. And in this technique, they're also using a droplet dispenser similar to the last technique to generate a stream of identical droplets. However, in this case, they're going to illuminate that droplet with a light sheet and then collect the light through a horizontal slit before it makes it to their camera. So they're only collecting the perpendicularly scattered light. They're going to collect their scattered light around the rainbow angle, which for their size droplets was about 142 degrees. And if they know the refractive index of their droplet, which they do because they can measure the bulk property of the solution that they put into their droplet dispenser, then the scattering angle is going to be related to the droplet's aspect ratio. And so what we see here on their CCD image is every one of the rows is a picture, is this rainbow scattering of a droplet. And then as we move down the CCD image, we are moving down in time, which is the difference in height from where the droplet was generated to where they're snapping the photo of the scattering. And so they can use this scattering angle to work out what the aspect ratio of the droplet is. And then they can use this change in aspect ratio as a function of time or height to determine the oscillation frequency of their droplet, which goes into the same surface tension equation that we were using previously. So this rainbow refractometry technique is able to measure, or that there's an example of measuring equilibrium surface tension for soluble solutes and organic liquids. But in theory, it's also possible to look at surface tension dynamics. For the droplets that they were studying, these are quite large at 150 microns. They were looking at like row to row on their CCD of about microsecond resolution. And then the whole thing, we're talking millisecond timescales. But of course, as we move to smaller and smaller droplets, we are going to see those oscillations damp faster. And this technique really relies on transparent solutes in order to see this rainbow refractometry. Again, because we're using droplets that have been generated from this droplet dispenser, and then we're starting to image them right after they've been dispensed, we're going to be limited to subsaturated solutions and to low viscosities. Another technique that has been used, getting used quite extensively now, is quasi-elastic light scattering, or QELS. And this technique also is going to look at these surface oscillations on droplets. However, it relies on small thermal fluctuations that can perturb the droplet air interface. And these oscillations are very small, on the order of angstroms, but at a spherical interface, the resonant frequencies of the droplets can be observed. And so in this example here, they have the droplet trapped in an electrodynamic balance, but they have also shown this to be possible in an optical trap. And so they use a laser here. This is their quasi-elastic light scattering laser, and they collect on the other side here on a photodiode. And the spectrum analyzer will give them a spectrum that looks like this. We have our intensity as a function of frequency, and we can see the L equals 2, L equals 3, and L equals 4 modes for this droplet. They can determine the surface tension for all of these modes and find the best fit surface tension for all of the modes simultaneously. Now, one really cool experiment that has been done with this QELS is looking at the phase change of aerosol by watching the change in surface tension. So they have a mixture of ammonium sulfate and PEG. And if they start at low relative humidities or lower relative humidities, around 80%, they measure surface tensions that are right in line with pure PEG surface tension. However, when the relative humidity is increased to about 86%, all of a sudden they see this drastic step up in surface tension. And now we're measuring surface tensions that are going to be of this like well-mixed ammonium sulfate, PEG, and water droplet. So this was the first example of seeing this change in morphology. So going from a phase-separated droplet into a well-mixed droplet and being able to monitor that change by surface tension measurements. I'll also note here that Jacobs et al. Has recently used the same technique to look at the size and concentration-dependent surfactant partitioning in droplets. And so if that's something that's of interest to you, I recommend that you take a look at their paper. This quasi-elastic light scattering has also been used to look at the surface tension of aerosol extracts. So this was an example that they did in the electrodynamic balance. Because they're in the EDB, they don't need to worry about the trapping laser absorbing they don't need to worry about the aerosol absorbing at the trapping laser wavelength. But they did require the addition of very high salt concentrations in order to keep that droplet stable in their trap. So In the aerosol extract, there was, I guess, a lot more organic than there was salt, and so then their droplet would just evaporate when their relative humidity was stable. And so they added quite a bit of salt in order to keep that droplet stable. And the addition of salt can lead to salting out of surfactant. So we need to be careful when we are drawing conclusions from aerosol extract data. If we've added a bunch of salt to it, that surface tension might not be actually relevant to atmospheric aerosol if the salt composition is different. Again, we also need to remember that an extract of aerosol is an ensemble average of all of the aerosol on the filter, and so it doesn't accurately represent the surface tension of individual aerosol droplets. So quasi-elastic light scattering is able to measure the equilibrium surface tension for soluble solutes, organic liquids, and surfactants. We can work with quite small sample volumes. So right now, the lowest radius that has been looked at is about 4.7 microns. If we're working in an EDB, we can look at either transparent or weakly absorbing solutes. If we are working in the optical trap, of course, we're going to be limited to those transparent solutes. We could work with supersaturated solutions, and as we saw in the previous example, core shell morphologies and phase transitions can be monitored here. One shortcoming or difficulty this technique has is that we are limited to low viscosity. In this example, McCarthy et al. Looked at surface oscillations of sessile droplets, and sessile droplets are droplets that are on an interface. And so they had a droplet dispenser, and they had those droplets being impacted on the surface, and then they used high frame rate imaging to watch the surface oscillations as a function of time. And because we're working with a sessile droplet here, the denominator of our equation, this term that has all the L values in it, has to be modified. And it turns out that that modification requires knowledge of the contact angle between the droplet and the interface. And they were able to actually measure that using these same images. So once the droplet stopped oscillating, they could use image processing software to measure the contact angle from one of their images. So that wasn't too big of a problem for them. What a bigger problem was that when the surface tension is low, the droplets tended to spread out on the surface quite quickly, and so they couldn't observe too many oscillations, making the Fourier transform a little bit less reliable. They also saw viscous damping when the viscosity of the droplet was large, and this also limits their accuracy. So that's what we see here on the image on the right-hand side. On the top, we have the surface tension of water ethanol solutions. We can see the bulk literature values, the black line, compared their method to the stroboscopic imaging technique, which are the blue triangles, and then the red squares are their high frame rate imaging of these droplets on surfaces. We can see this discrepancy as the ethanol concentration increases and the surface tension falls below about 40 millinewtons per meter. And then on the bottom here, this is for sucrose droplets, so water and sucrose. Sucrose actually increases the surface tension as the concentration increases. But as you can see, when they got to 30% sucrose, we have these gigantic error bars for the surface tension due to that viscous damping. So this high frame rate imaging of droplets impacting surfaces technique is able to measure the equilibrium surface tension for soluble solutes. They were working with small droplets, but still maybe greater than picoliter, so we're in the tens of microns radius range. We have the potential to look at transparent or light absorbing solutes. And this technique, unlike many of the others, has the advantage of being able to observe additional processes for the same droplet. So for example, because we have one droplet on a cover slide, you could also watch that droplet crystallize or take it for some other kind of analysis after the fact. Some of the downfalls or the difficulties with this technique are that the low surface tensions were very difficult for them to measure accurately. So for their 20 micron radius droplet below about 40 millionths per meter, started to see these uncertainties, these discrepancies. They could look at only subsaturated solutions, and then again, low viscosity because they're using that same droplet dispenser to generate their droplets. Okay, so the last technique that I'd like to talk about is this electric field-induced shape oscillation technique. And in this technique, they are still relying on these surface mode oscillations. However, they're going to use an electric field in order to generate these. So they have their droplet trapped in electrodynamic balance. And then they also have an additional field which they can scan the frequency of. And they're going to measure the phase shift between their input frequency and their signal. And they're going to fit this curve with a line. And when the phase shift is equal to 90, this is the resonant frequency, which goes into the surface tension equation up here. So their surface tension in this case depends on the radius of the particle as well as the density and that oscillation frequency, but it also depends on the charge. And this is true any case when we're working in an electrodynamic balance. In order to hold a particle in an EDB, that particle has to be charged, and charges at the surface can impact the surface oscillations. So that needs to be taken into account. Now, what is really cool about this technique is that in addition to measuring their surface tension and their EDB, they've also added a cooling stage. And so they're able to measure the surface tension as a function of temperature, in particular in the supercooled region. So in this example, they're looking at the surface tension of water, and we see their highest temperature measurement is below 0 degrees Celsius, and they continue down to about negative 30 degrees Celsius. And they're able to reasonably accurately determine the surface tension of these water droplets as a function of temperature. So some positives of this technique are, again, the small sample volume. In their example here, they were looking at 50 micron radius droplets, but this was just the first proof of concept paper. So they can definitely go to smaller droplets. Because they're in that EDB, the potential for transparent or absorbing solutes is there. Because they have their cooling stage, they can look at super cool droplets, but they could also dry droplets out and look at supersaturated droplets. And it could also be possible to look at droplets with a bit higher viscosity here. A couple of things that make this one a little bit difficult are that it's going to require knowledge of the droplet charge, which is possible to measure with an electrodynamic balance, but is an additional step. And their current iteration does not have any sort of relative humidity control, but that should be easy to overcome in the future. So just to finish up here, I'd like to talk a little bit about some of my perspectives and conclusions about the field of aerosol surface tension as we stand now. So one of the first things that I'd like to mention here is that the surface tension measurements sometimes have very large uncertainties on them, and we would like to be as precise as we can, of course. And so what are some methods that we could use to minimize the uncertainty on our aerosol surface tension measurements? Well, one thing I'd just like to point out here is that, at least for these surface oscillation methods, our surface tension is dependent on radius to the third power. And so the uncertainty on the radius is one of the biggest uncertainties on the surface tension once we propagate through all of the different uncertainties. And so what this means is that as the droplet size decreases, higher precision in the droplet radius is needed in order to reduce the uncertainty on the surface tension. And we have a bunch of different methods at our disposal to measure the size of aerosol droplets. So for example, we could look at the angular scattering, our Mies scattering. We could look at the positions of our whispering gallery modes, also Mies scattering. But something that is used on occasion, mostly for larger droplets, is to just look at the geometric size. So if we have a calibrated pixel size on our camera, we can then use edge detection to determine the size of a droplet. Now, this plot on the bottom is comparing the uncertainties on surface tension determined from Mie resonance radius determination compared to optical imaging radius determination. And in both of these papers, they used quasi-elastic light scattering. And so there shouldn't be anything too different about these two techniques that should give us different uncertainties. The biggest difference here is the way that they determined the radius of their particles. So we see when they use the Mie resonances, we have quite low uncertainties on our surface tension, below 5 millionths per meter, maybe more like 2 or 3 millionths per meter. However, when they use the optical images, for the very large particles, the uncertainty is maybe about 5 millionths per meter. But as we go to smaller and smaller particles, that uncertainty increases dramatically. And this is because when we're using the size based on a calibrated pixel on our camera, that calibrated size doesn't change as we move to smaller and smaller droplets. And so the percent error on the droplet radius actually increases as we go to smaller sizes. And so this is just something to keep in mind. If we want to more accurately determine surface tension and we want to move to smaller droplets, it would be a good idea to maybe use one of these Mie scattering techniques to determine the radius rather than a geometric size determination. So summary. We have a lot of different surface tension measurement options at our disposal. And so which one are we going to choose when we want to do a surface tension measurement? Well, I would say that there's not one perfect technique out there that is going to be useful for every single measurement we want to do. And so the things we need to consider are, what is the size range of aerosol we're interested in looking at? Do we want to investigate equilibrium or dynamic surface tension? Do we care what temperature the measurement is taken at? Are we looking at concentrations that are above or below the saturation level? And does the solute in our droplet absorb light, or is it transparent at a laser wavelength? And so what do I think are sort of the next things that this community can do now that we have all of these different surface tension techniques at our disposal? Well, there are not very many measurements in supersaturated aerosol right now. So that's definitely an area that could be further investigated. Supercooled aerosol is another big sort of open question. The one example that I showed you today is, as far as I'm aware, the only example in the literature. There are also open questions about complex mixtures and ambient aerosol. And so thinking about things like, how does pH affect aerosol surface tension, and thinking about how brown carbon aerosol or biomass burning aerosol might have surface active components is also a region for experimenting. So with that, I'd just like to say thank you to my group in the top here and the team at the University of Bristol, where I did my postdoc, especially Brian Bizdek, who started me on this journey into aerosol surface tension. I'd like to thank Oregon State University for their support, and Aerosol Science and Technology for providing the headline graphic that you saw today. And I'm happy to take any questions.
Thank you for that wonderful presentation. I really enjoyed it. And now we can take questions. If you have a question, please raise up your hand in the chat box, then you can unmute yourself. And if you can also drop your question in the chat box as well, it's really appreciated. Thank you. I think you have a question from the chat box. It says, when you say low viscosity or higher viscosity in the case of electric field induced, in case of electric field induced oscillation, how high or low are you talking about in the order of magnitude?
Yeah, that's a very good question. I don't have a number off the top of my head. Glassy aerosol, I think, is going to be completely out of the question. It's going to be very difficult to induce any kind of change in shape in something glassy. But maybe something like a concentrated sucrose droplet might be doable.
Thank you. We have another question. What's the smallest droplet size that can be measured by this method? Yeah.
Yeah, so the AFM method is the only method that can get, as far as we have seen so far, the only method that can go to sub-micron aerosol. All of the methods based on optical traps or EDBs, about 4.7 number that I put in there, that's about the smallest. And then the methods that rely on a stream of identical droplets generated from this piezoelectric droplet generator. Those droplets tend to be maybe about 10 to 20 microns in radius. And this is because the orifice of those droplet generators is going to limit the size of the droplets that can be formed reliably. And those tend to come with a minimum of a 10 micron size orifice.
Thank you. We have another question. Are there any current capabilities or key limitations when it comes to measuring the surface tension of aerosols or cloud droplets in situ from airborne platforms?
Sorry, can you repeat the question?
Are there any current capabilities or key limitations when it comes to measuring the surface tension of aerosols or cloud droplets or cloud droplet in situ from airborne platform, like in situ observations?
Yeah, in situ, I don't think I have a single example. Probably the AFM technique would be the closest thing, but you have to collect the aerosol or the cloud droplets onto a substrate and then put them under the AFM after the fact. Any of the other techniques that are measuring like ambient aerosol, they're all extracts, right? And so this is always going to be an ensemble average and doesn't get to the fine detail of single cloud droplets.
Thank you for that response. We have another question. What did you use to image the coalescence of droplet aerosol particles?
So in that experiment, we are just using a CMOS camera to actually image or like visualize the coalescence event. But that CMOS image is not used in the analysis. That's just kind of for our own seeing of what's going on. The two key pieces of information that we pull from that experiment are the elastic scattered light, which we're collecting on a photodiode, and then reading out as a function of time. And then also the cavity-enhanced Raman spectroscopy, which we read out through a spectrometer and CCD chip.
Thank you. We have another one. When using AFM, what is the reason to use a special tip? Can you use regular AFM tip?
Yes, so there is one example of using a regular tip. I think if we use a nano tip, we could go to a smaller size because we're going to indent the droplet. We don't want to just like smush the droplet. But there are examples of just using a regular AFM tip now as well.
Thank you. I think we have, how can we convert solute concentration to solute mass fraction as shown in, I think slide 17.
Why did I use that? So personally, I like to work with concentration, but in atmospheric science, often mass fractions are what can be pulled out of analysis. And so I think both of these concentration units have use, and sometimes it's nice to see both of them together.
Another question says, with the droplet deformation method, how difficult is it to balance the force from each beam to ensure simultaneous stable trapping of a particle in both beams?
Yeah, so in that experiment, they split the laser beam. So they have one laser and they split the laser beam into two using a beam splitter. And then before the experiment, what they will do is measure the intensity or the power of both beams. And they can use a polarizer to slightly change it. So when the light goes through the polarizing beam splitter, it'll be split into the two polarizations. They measure the power of both of those beams, and if they're not equal, you can change the polarization until those two beams are equal.
Thank you. If you have questions, please, you can unmute yourself to ask. But I think that's all for now on the chat box.
I have two questions. Can I ask?
Sure. Yeah, please, you can go ahead.
Yeah. Thank you, Addison, for your great presentation. I have two questions. First is about the holographic optical trapping. So as far as I know, it's uh, collision and coalescence of two droplets. So I'm wondering if the systems are containing surfactants when they come to each other and coalesce. Uh, how long does it take for the surfactants to partition on the surface?
So by the time we have coalesced the droplets, they have already been in the optical traps for probably a minute. They also had some time from when they were nebulized to when they got to the optical trap. And so those droplets should already be at their equilibrium surface concentration before we do the coalescence.
So when they're coalesce, I mean they're damping, right? There would be an oscillation, or like damped oscillation. So, and then you start like measuring the surface tension of that damping particle, the newly formed droplet. So at that newly formed droplet, how confident you can say that surfactants are still on the surface? Because particle is still oscillating, right? It's
Yes,
damping.
yes. If there was no surfactants on the surface, then we would expect to retrieve the surface tension of just the co-solute perhaps. And we
True.
retrieve surface tensions that are much lower than that. So there's definitely surfactants on the surface.
True. So I think there must be a relation between your second paper and that in JAX, I suppose, where you measure the equilibrium times, I suppose. I think it's around some microseconds, but in the holographic optical tweezer, the time that you need is about milliseconds, right? Can we conclude that the partitioning time is so quick, so this would be the reason?
So these are two different processes. One is total generation of a new surface, and one
Okay.
is coalescing of two droplets that already are at surface equilibrium.
Okay, I was thinking maybe that newly formed droplet is also can act as a new surface. Okay,
It can,
thank
but
you.
it's not a completely empty surface at that
Yes,
time.
good. Yeah, I got it. My second question is a bit general about the atmospheric importance of surface tension. So as we all know, Kohler theory suggests that the surface tension has nothing to do with the activation process. So there are many papers that says that no, it's not true. So especially in surfactant containing systems, it could affect. But the thing that I know is mostly about the very small size droplets, like several nanometers. The surface tension of several nanometers droplets can affect the activation process. And on the other side, the surface tension is a size dependent parameter, especially when the surface area to volume ratio increases. It's hugely, I know, I don't know, I think that there would be a difference between the surface tension of a micron sized droplet and that of a nano sized droplet. So my question is that why do we actually measure the surface tension of micron scale droplets?
So the reason we've been measuring the surface tension of micron scale droplets has been to test and validate the predictions of surfactant partitioning models, which utilize the surface area to volume ratio of the droplet to predict surface tension. So until these measurements of aerosol surface tension at the micron size were available, they had only been comparing these partitioning models to predictions of cloud droplet formation. So like the critical supersaturation, for example. But there are multiple processes that are involved in that. And so it's not as useful as a metric to compare those models to as direct surface tension measurements are.
Sure. Thank you very much.
I think we have some questions in the chat box. And it says, in the 80s, we detected surface-coated nanometer aerosols by a so-called multi-step condensation nuclide counter. wouldn't this be a chance to extend the range to really small particles, e.g. soot, for example, like soot also?
I'm not familiar with this technique or this work, unfortunately, so I don't think that I am qualified to comment on that, but it sounds like an interesting idea for sure.
Okay, may I add something? May I add a question to that?
Yeah.
Okay, what we did at that time, Christoph Hesper and me, is to use an old Nolan Pollack condensation nuclear counter. And this was fed by monodisperse nanometer particles and at different coatings. So we produced aerosols with different C16 surface active material, organic material, but the outer electrodynamic diameter was always the same. And that was checked by this multi-step condensation nuclear counter. And depending on the degree of surface active material in or a closed surface by different materials with different contact angles, then the onset of a condensation could be clearly observed and measured. So at that time, of course, we were not interested in the surface tension. We were interested in the coating. Exist there particles with organic coating and so on. But on the other way around, it should be possible to use that to answer your questions, mainly in a range below 10 nanometers, because all the carbon particles and so they are mainly there.
Yeah, I think with the inverting the partitioning model, we might be able to come up with a surface tension. It's very interesting. Thank you for your comments.
I think we have one final question. It's a person asks about optical trap method. Are the droplet held in equilibrium with the surrounding relative humidity? And how do you characterize or confirm that the droplet has reached equilibrium under those controlled RH conditions?
Yeah, so there are different ways that we can work with this. We could definitely look at a droplet that has come to equilibrium, and we can monitor this by watching the positions of the whispering gallery modes. And we can use those in order to do the refractive index and the radius, right? So if the particle is still growing or shrinking, we know that it's not at equilibrium with the surrounding air. If the refractive index is changing because of water uptake or water loss, of course, it's still not at equilibrium. So this is one tool that we could utilize. Alternatively, we don't have to necessarily wait until the particle reaches equilibrium. And after we are finished with our experiment, we can go back and look at what the refractive index of our droplet is, and then use a model to turn that refractive index into a droplet composition. And so we can determine the composition from the refractive index in both cases, but we don't necessarily have to be at equilibrium with our surroundings in order to know what the composition of the droplet is.
Thank you. I think that's the end of the questions. So I hand it over back to Amy. Thank you for the presentation. It was really insightful. Thank you.
Well, thank you, Allison Tewu. This was a really great lecture, and I hope you all enjoyed it, and we look forward to having you join us again next month. Thanks, everyone.